In the quantum realm, people have different kinds of, the systems have different kinds of behavior, right? The same system can behave like a wave for some experiments and like a particle for certain others, right? So this is what is called as a wave-particle duality, right? And there are many people who had spoken about this, Louis de Broglie, for instance, and Paul Dirac, and so on and so forth. So this, along with some of these other, so one more thing which was very different was, of course, that the parameters, the variables that a system had could only take certain discrete level values, right? It could not take a continuous level value, so to say. There was obviously the element of superposition that we had already spoken about. And there was also this idea that whether there is a reality to what we are seeing, because if a certain system can exist in multiple states, what can we speak about the objective reality of it, right? Is there actually a reality or not, right? And the last part, which was very interesting in the quantum realm, was non-locality, right? Things could remain connected to each other even if you were to spatially separate them apart and, let's say, take them to different galaxies, right? How was this possible, right? Because Einstein's relativity talks about the speed of light, and that things which are very far apart cannot necessarily communicate instantaneously, but there was a certain instantaneous aspect to this. So non-locality became a very interesting part of this connectedness, right? It comes back to this idea which we were talking about in Shaiva Darshan, so to say, right? So quantum logic, when we talks about superposition, talks about the observer's effect. It talks about the transcending the binary distinctions, right? They can be just not the yes or no or specific states, but a multiplicity of states are possible, right? Then there is also this aspect of non-commutativity. What does that mean? It means that if you were to go in a sequence of steps, right, and then you were to reshuffle the steps, right, would you get to the same result or not, right? Quantum mechanics says you won't, right? In Trika Shaiva Darshan, you would also say you won't, because the way in which Shiva and Shakti work together to create, to co-evolve this world, that the universe that we see, has a certain very distinctive aspect to it, right? It has a very distinctive trajectory, so to say, right? So therefore, this non-commutativity is also in a manner seen within the Trika Shaiva metaphysics, so to say, right? So there's a very interesting way in which the quantum logic and Trika Shaiva Darshan come together. So when we talk about quantum physics, and this is a very important part, we talk about entanglement. You all may have come across this term within many popular science lectures and talks. Entanglement is basically this idea that things are interconnected to each other, connected to each other in a way which defies spatial separation also, right? So this idea of entanglement came from a series of debates between these two gentlemen you see out here, Bohr and Einstein, right? So Bohr and Einstein had this fundamental debate on the question, is nature fundamentally deterministic, right, or probabilistic? Does it have an aspect of chance to it? Is it actually something you can determine completely if you were to given the rules and the parameters that are relevant to it, right? So Albert Einstein, along with two of his colleagues, had put forward this idea that, certain things seem to defy the classical way of thinking, right? They are still connected when you separate them, and they relate to this idea of entangled states, right, which he had postulated in 1935 in a thought experiment. And mind you, it was basically to negate this broader trajectory of quantum physics that he was not very happy with, which we have already discussed about, right? And so in this, there was a team in 1950 which first saw entangled particles, right? They saw particles which came out from a collision experiment, and they saw that they had certain kinds of correlations, connectedness, right, which existed in the properties of the particles, right? So Leonard Susskind, who's a very well-known kind of physicist at the moment, he has spoken about this, and he has said that these debates with Niels Bohr were a notorious love-hate relation, right, with the subject. And I think shared by a growing number of physicists is this attitude does not do justice to the Einsteinian view, right? Because Einstein also had many aspects which he was trying to put forward. He said that there may be some variables out there which we do not have access to. If we had access to those variables, we would have been able to explain everything in terms of classical physics, right? Because we don't have access to that, that's why we are seeing this whole business of chance, of probabilistic definitions of reality, right? So this whole dialogue was a very interesting part of how entanglement and quantum physics evolved. And that went forward only in 1964 did this British physicist finally come to this idea that no, physics at that quantum realm is fundamentally probabilistic, right? And Einstein's idea of hidden variable theories is not quite correct, right? So there was an experiment that was undertaken, and he had assumed this idea of realism, locality, and free will, right? Realism in the sense that whatever you're measuring has a reality to it. Locality in the sense that whatever you're measuring at some point does not have an instantaneous or an immediate effect on something which is very far away, so it's localized. And free will is that if I were to do an experiment, I have the free will to decide how I do that experiment, right? So these three aspects kind of brought together this idea of Bell's inequalities. So I wouldn't go into too much on that, but this was proven in experiments, and in 2022 the Nobel Prize was given in physics for proving this in an experiment, so to say, right? So this was a major accomplishment in a manner of speaking. So quantum entanglement, Einstein called it spooky action at a distance, right? Abner Shimoni, who was another physicist, he was more poetic in some ways. He called it passion at a distance, right? So there were many ways in which people talked about it. In the 1990s, it was spoken of in terms of entropy, right? This idea of disorderliness, right? And later on, as we went forward, it was spoken of in terms of how it can be used, right? So in terms of cryptography, for instance, in terms of dense coding, in terms of teleportation, there's this idea of quantum teleportation. And so the definition of entanglement is that we cannot speak of a collection of particles in terms of the individual particle states. We have always should be talking about the global state, the composite state as one, right? So it cannot be spoken of in terms of reductionist approaches. That's the idea, right? So I have given a small image of the entanglement experiment. This is the first real-time imaging of entanglement, and I hope you can have a look at this, which gives you an idea about how entanglement is generated. So you see here different light specks. These light specks on the two sides, the two big collection of lights that you see, there are two different light particles which are complementary. There are sets of two, right, which impinge the screen, and they are entangled in their properties, right? So this is one of the experiments which was done in Vienna in Austria that showed us entanglement. So entanglement can be manipulated, can be used for broadcasting purposes. It can be used for different kinds of measurements and applications in protocols, in quantum information, for instance, right? So I've given some of these, the ways in which it has been used. But we won't be kind of looking into that all that much, because that relates more to the application side of it. Whereas in this talk, I would like to keep to the fundamental aspect of entanglement.